For anyone keeping an eye on cellular longevity research, these senescent cells are always popping up. They're kind of a big puzzle, aren't they? These older cells that just stop dividing but hang around, causing issues. And for ages, we've seen they get, well, bigger. But what if that size isn't just a side effect? What if it's actually key to how they stick around?
Exactly. We're talking cellular senescence.
Mm.
Cells that are, basically stuck. They won't die, but they're not doing their job properly either. And yes, a key feature is that they're significantly larger than younger, healthier cells. The big question has always been, how do they actually support that large structure? It's quite an architectural feat for a cell. Today, we're looking at some really fresh insights into the molecules behind that.
Right. And we've got a great source for this deep dive. It's a new study just out in Cellular Signaling, March 2025. And it seems to pinpoint a really crucial protein involved not just in senescence, but kind of amazingly in cellular rejuvenation too. So our mission today is to unpack what they found about this protein, AP2A1. What does it tell us about aging at the cellular level? And maybe, just maybe, how we could influence it. Let's get into it. Okay, so AP2A1. What did this study actually find it's doing in these senescent cells?
Well, the big finding is that AP2A1, that stands for alpha-1 adaptin subunit of adaptor protein 2, quite a mouthful. Its levels are way up in senescent cells, highly upregulated. Think of these adaptins as like the cell's internal sorting office, making sure proteins get delivered to the right place. And AP2A1 isn't just present in higher amounts. They found it specifically clustered along these enlarged stress fibers inside the cells.
Okay, so it's not just there randomly. It's positioned quite deliberately. The stress fibers.
Hmm?
Those are like the cell's internal scaffolding, right? And the study didn't just observe this, did they? They actually manipulated AP2A1.
That's the really exciting part. They showed that if you reduce the amount of AP2A1 using techniques like knockdown, you can actually reverse some of those key signs of senescence. The cells start looking, well, younger, rejuvenated in a sense.
Wow.
And conversely, if you take young cells and force them to make more AP2A1 than usual, you actually push them towards becoming senescent.
So it really does look like some kind of molecular switch.
It strongly suggests that, yes. An on-off switch, potentially, for this aging state. And importantly, they saw similar effects in different types of senescent cells, too. Whether induced by UV light or drugs, different cell lines. It seems pretty fundamental.
A fundamental switch for aging or rejuvenation.
Yeah.
That's pretty significant. But how? How does AP2A1 actually manage this? What's a mechanism that lets it maintain this big, stubborn cell structure?
Yeah, so this is where it gets into the cellular mechanics. They found AP2A1 physically interacts with another key protein called integrin beta-1. Integrins are crucial. They're like the cell's feet or anchors, helping it stick to the surface it's sitting on. The extracellular matrix.
Ah, okay. So AP2A1 and these anchors are working together.
Exactly. They observed both proteins moving together in a very coordinated way along those internal stress fibers we mentioned. Now, senescent cells are known for having these really enlarged focal adhesions. Think of them as super strong attachment points where the cell grips its surroundings. And they have a much stronger grip overall.
Right. They're really dug in.
Precisely. The idea is that senescent cells maintain their large size partly by reinforcing these anchor points. And AP2A1 seems to be the key player directing integrin beta-1 efficiently to these spots, using the stress fibers as tracks. It's like trying to secure a huge old structure. You need really strong, well-placed anchors, and you need someone constantly checking and reinforcing them. AP2A1 looks like that crucial coordinator.
That makes a lot of sense. So it's actively managing this stickiness to support the large structure. They're not just big, they're actively maintaining being big and anchored. Okay, so translating this, what does finding this role for AP2A1 actually mean for us, practically speaking?
Well, it flags AP2A1 as potentially a very important marker for identifying senescent cells, and maybe even more excitingly, as a direct target. If you can modulate AP2A1, perhaps you can modulate senescence itself.
Right. So pulling this together, then, the core idea is AP2A1 is like the architect maintaining the structure of these old and large cells. And it might even be the switch to flip them back towards a younger state. It really makes you wonder, doesn't it? If we could get really precise control over this protein, understand its on and off states, what could that mean for tackling age-related decline?
Exactly. That's the big picture implication. If AP2A1 holds up as this reliable marker and, crucially, a druggable target, it really does open up some potentially revolutionary paths for research. You start thinking about therapies targeting senescence, not just to treat diseases after they appear, but maybe to promote healthier aging overall, to keep cells functioning better for longer. So the question for you listening is, how might this kind of deep dive into basic cell mechanics fundamentally change how we approach longevity? Not just adding years, but adding healthy, vital years. It's certainly something to think about.